Hi, I'm Adriano Poci from Durham University, and today I'm going to be talking about measuring the assembly histories of local external galaxies using a combination of orbit-based dynamical modeling and many of the measurable stellar properties. So I'm going to start with what's routinely done for measuring the assembly histories of external galaxies. So at the top in black, what you see is just an example integrated spectrum of some external galaxy, and in red is the fit to that spectrum using a series of stellar population models. Then the ingredients that go into this model are shown at the bottom, which are in this case the phase space of stellar metallicity and stellar age. And the color indicates the weight given to each region here. So you can see that this spectrum is pretty old, and there's evidence for two distinct populations in metallicity. So this constitutes a conventional star formation history, and these techniques have been routinely applied to spectroscopic data. Then with the advent of integral field units, we could do these measurements, these fits at every spatial location. So what I show here is the projected mean stellar metallicity map. And what this shows very clearly is that in this galaxy, the metal-rich stars exist basically in the disk and also peak towards the center, while the metal-poor stars are basically out of the disk plane and towards the outskirts. So it's important to note that we measure luminosity-weighted mean values in this work, which means that through each line of sight, it is the brightest populations which contribute the most, not necessarily the most massive. Now, this is also implicitly the case for the stellar kinematics. So what I show here is just the mean rotation velocity. And it's clear then that the kinematics which we measure in the disk plane, for instance, are dominated through the line of sight by these same metal-rich stars, while the kinematics we measure off the disk plane are dominated by these metal-poor stars. And so I say this is implicit because it's not really discussed that often in the context of stellar kinematics. But even so, it's difficult to take into account this connection if we want to, for instance, run a dynamical model of stellar kinematics. So I think this highlights two inherent limitations with the current approach. And they are firstly that we're always dealing with projected quantities because the measurements are always integrations through the line of sight. Secondly, there's some apparent connection between the measured stellar kinematics and stellar populations, which we would like to take into account when we're modeling them. But also this alludes to possibly some intrinsic connections between the populations and dynamics, which we would also then like to tease out of the same models. So I'm going to explain our methodology, and it's going to be in the context of the galaxies that we've applied it to. So I'll start with the galaxies themselves. What I show on the top row is photometry from the Fornax Deep Survey using the VST of 3 edge-on lenticular cluster members of the Fornax cluster. And what's shown in the brown dashed outline is the field of view of the MUSE data we have from the Fornax 3D survey. And then what's shown at the bottom is another edge-on lenticular galaxy, but this time from the field. And so just keep these in mind as we're walking through the method and the results. So the method is based upon a Schwarzschild orbit superposition dynamical model. And so this orbit takes a whole bunch of a diverse range of numerically integrated orbits, and I illustrate a few here. These are shown in projection just for illustration. So this is spheroidal, toroidal, or disk-like orbit. And then we try to find the best linear combination of these orbits which reproduce the galaxy. And in this case, by galaxy, what I mean is the measured kinematic moments. This is also a well-established technique, and we apply it routinely to our measured kinematic data. So what I show here on the top row from left to right is the projected surface brightness, mean velocity, velocity dispersion, and higher order Gauss-Hermite moments. Then on the bottom row is the fit from the Schwarzschild model to all of these data. And now, so what's in this model is a whole suite of orbits for which, from which we know their intrinsic kinematic properties. So we can actually start to look at this model from an intrinsic perspective. So one such parameter is the circularity, which I show here on the vertical axis. And the circularity is a measure of the angular momentum around the short axis of the galaxy, normalized by that of a circular orbit. And so circularities of 1 or -1 are circular orbits, which are co or counter rotating. And circularities of 0 are basically pressure supported orbits. So I show circularity as a function of radius, and the color indicates basically the distribution of orbits for this galaxy model. So this particular galaxy has a strong presence of a low radius, low circularity component, which is analogous to kind of like a classical bulge. Then as we move out in radius, we start to pick up disk-like orbits, which have high angular momentum. So now we'd like to take these orbits, which reproduce the stellar kinematics, and also be able to reproduce the stellar population maps. Now to do this, we take a rather simple approach of just gridding up this space. Now, before we proceed, I can actually show how this space behaves. So if I just isolate one cell here, let's say low radius, low circularity, what I show here is for just these orbits, the projected surface brightness, velocity, and velocity dispersion. And you can see that this region is spheroidal and completely dispersion dominated. Then at large radius and high circularity, we have basically a projected disk that's dominated by rotation. So then without getting into any of the mathematics, we take these cells in circularity space and try to reproduce the projected stellar populations just like the stellar kinematics. So this is the outcome for the mean age on the left, mean metallicity on the right, for the measurements from spectroscopy on the top row, the model in the middle, and the residuals at the bottom. And what this indicates is that the orbits do a good job of also reproducing the stellar population maps. And the outcome here is that we have this suite of orbits with known intrinsic kinematic properties, but also now which each have their own age and metallicity. So we can start to pull apart the galaxy from population properties, not just kinematic properties. So what I show you here now on the left are different bins of age. And what's shown is just the projection onto the sky of all the orbits within each bin. So you can see that the old orbits are concentrated towards the center and they're basically spheroidally distributed. As we move to younger and younger ages, we start to see the disk pop out. Then the metal-rich stars are basically in a disk and also concentrated towards the middle. And the metal-poor stars have very little spatial structure. But now we have actually, as I mentioned, a whole bunch of intrinsic kinematic properties that we can also look to correlate with these population properties. So what I show here now on the vertical axis is the vertical component of the three-dimensional intrinsic stellar velocity dispersion from the model. And I've isolated just the disk-like orbits. So these are high circularity. And I show this as a function of the age that they've been fitted with, or equivalently on the bottom, their formation redshift. And what this correlation shows is that from old to young stars, the orbits become more disk-like. So there's less motion out of the disk plane. Now I mentioned we've done this for all 4 galaxies. And so I can show you all of their results together. And the trends are rather consistent for all of them. Now, what's really powerful, I think, about this technique is that at the same time, we can compare without any recalibration or anything, measurements directly from, for instance, the Milky Way. So this is what I show here. The dots and pluses are on and off the disk plane of the Milky Way, and they're separated at 70 parsec. And these data are from you et al. And now, because these are the same physical measurement, any offsets in these planes should have also a physical origin rather than a modeling offset. And so I think this is probing really the differences in assembly histories directly, which is precisely what we wish to measure. Now, what I can also show are measurements of the gas velocity dispersion. So these are shown in the box whisker plots, and now these are actually not strictly comparable in the sense that these are gas, not stellar measurements, obviously, but also that these are direct measurements at each redshift, whereas the Milky Way and our stellar models are archaeological. So we take the redshift 0 configuration and we infer their history based on their present day properties. But I think there's actually still quite a lot to learn here, because if we look at, for instance, the old stars from our model, these stars have had to experience the entire evolutionary history of their host. So if we then compare those to gas measurements at the epoch from which we believe the stars formed, then these differences should tell us something about their history that they've experienced over the entire intervening time. So I think this is a very powerful plot, but we found evidence that it's not actually the whole story. So now all of the investigations so far of this age velocity dispersion relation have been marginalized over metallicity. So every point here can just be any metallicity. But we found evidence from our model that actually metallicity could have an impact. So to investigate this, what we did is now I'm showing you the same age velocity dispersion relation, where each panel now is for one of the 4 galaxies that we've looked at, but each curve within each panel is a different bin of metallicity. And inset in the text are the correlation strengths computed for all the curves within a single panel. And what this shows is that once metallicity has been taken into account, there's very little, well, the trend considerably decreases in significance of the age velocity dispersion relation. And this was a bit surprising. So as you might suspect, we looked at the opposite correlation, which is velocity dispersion metallicity at fixed stellar age. And this was also surprising because it indicates that almost independent of age, there is quite a significant correlation between the metallicity and the stellar velocity dispersion. Now, we interpreted this to mean to be indicative of for like a fixed star formation episode, a fixed period of star formation, more metal-rich gas will cool more efficiently and end up on dynamically colder orbits for the resulting stars. Now, this is, I think, another example of the power of this type of model, because such a correlation was only seen for the first time in the Milky Way just last year, and we're already finding consistent results for external galaxies. So I'll wrap up there just by saying I think we've produced a rather comprehensive and self-consistent model of the measurable stellar properties. We've measured the intrinsic age velocity dispersion relation for a number of external galaxies, but have seen that metallicity may play a key role. Looking forward, we're actually already working on incorporating spatially resolved maps of the stellar initial mass function, in addition to currently age and metallicity, and as always, to apply to more and more galaxies. Thanks a lot.